my video for the homework 4. Here I will show you that there's nothing hidden in the room. It's only me, the worksheet, and the formula sheet. Problem statements on the table. I'm not going to be quiet this time because it's kind of late in the night, but let's get started without further ado. Looking at the first refraction, we can know it's a Brewster's angle, and then you can use the identity that the incoming 90 minus theta 1 theta 1. This one gotta be theta 1 and 1 and 2. And over here we can say that 90 minus theta 1 equals to arc tan and 2 and 1. This is set it up by the fact that tangent 90 minus theta 1 equals to n2 minus theta n1 n1 sine 90 minus theta 1 equals to cosine 90 minus theta 1. Yep. So the eventual derivation is aimed at giving us this equation. And with this, we just plug and chug, and well, first we know 56.8 is the theta B Brewster angle. With that in mind, we could also know that n1 equals 1.13, thus n2 equals to 1.13 times tangent 56.8, which is 1.73. 1.73 is n2, which makes sense because it gotta be a number greater than 1, right, while not being an absurd number. Now it has two more refraction. Say we can now call, well, actually n4. N4 is a better name for this. So we'll change it to n4 because n2 is already given in the picture. Sorry, I didn't realize that. Yeah. This is the renewed version. We call it inside n4, the layer between n4 and n2 and 3, and n2 being the outermost layer. We know that n4 sine theta 1. This is because that angle is 90 minus theta 1. Actually, I'm gonna call it theta 4. The angle is 90 minus theta 1, which is oh yes, n4 sine 56.8. It's the same thing as this because theta 1 is given, and theta b, the browser angle, is 90 minus theta 1, which will give us theta 1 as the angle of incidental angle for the refracted one. The refracted one and the new incidental angle for the next reflection forms a right triangle, meaning this part has to be 90 minus theta 1, which is 56.8. And this would be n3 sine theta 3. Now we don't know what this is because, and this honestly isn't important because n3 sine theta 3 equals to n2 sine 90 degree. And because there is a total internal reflection, we could just say that n3 sine theta 3 equals to n2. This is a very important part because this will eventually give us the upper bound of everything. Well, upper bound of n2, which is one of the important factors we're looking for. Since we can see we got both equations equating n3 times sine theta 3, we can get n4 sine 56.8 equals to n2. Right, simple switching. We then get n2 equals to 1.73 times sine 56.8. Which give me 1.45. And this will be the upper bound. The reason why this isn't the lower bound is because n2 has to be a number such that it is smaller than n4 times sine 56.8, because essentially the equation we set it up here is n4 sine 56.8 equals n2 sine theta 2, right? And this will, oh, by the way, I'm going to show you the result here quickly. There's a calculation. It's quite simple in terms of math. And the important thing to set this as a lower bound is because, set this as the upper bound is because sine, this is essentially on the right side. And for any angle greater than 90, it causes total internal reflection, which is what we're looking for. And if n2 is greater than whatever is over here, this condition doesn't make sense. And I mean, well, physically, like just looking at the geometric, the greatest this is gonna be on the left side is having this equals to 1, so it's just n2 on the left side. So if this exceeded, it kind of just doesn't make sense and have to go to a lower sine theta value here. Well, with that in mind, we also know that the light speed is constant, and n2 equals to v2 equals c divided by v2, which is greater or equal to 1. This condition must be satisfied. So eventually we'll get an equation such that 1 smaller or equal to n2 smaller or equal to 1.45. And that will be it. Thank you for watching my video. Oh, and as a final bit, I'm just gonna show you everything I've done over here, just so you have a better understanding. Have a great day. Bye.